We've had our introduction to systems of equations, and during the introduction, we said we're going to need to solve systems of equations three different ways, one by graphing, one by substitution, one by elimination. We're going to look at the graphing method for this video. And in the graphing method, you're going to be presented with a system of equations. I just put in blah, blah, blah here. And what you're going to do is you're going to take this system, and remember, it has two different equations, equation 1 and equation 2. And you're going to graph both equations on the coordinate grid. So I'll just make something up here. Here's equation 1, la. Here's equation 2, la. And after you graph them, you're going to look for the intersection point. And an intersection point, like every point in the world of algebra, has a coordinate x comma y. Well, here's the great thing. If I find out the intersection point, I get an x comma y, and that x is the answer for x in the system of equations. That y is the answer for the y in the system of equations. So when we did our introduction, and we said, hey, for this system, x equals 5, y equals 2, that means if we would have taken the time to graph these, we would have found that at x equals 5 and y equals 2, one graph hit the other at that spot. Now this might not be an accurate graph, but you get the point. So here's what we need to do. Every time you have a system of equations and you're going to solve it by the graphing method, graph both of them, find that intersection point, and you're almost done. So let's start off with this example. We'll cover this up, it's secret right now. I have a system of equations and I'm going to solve it by the graphing method. Well, most people agree that y equals mx plus b is the easiest form of a line to graph, so I'm going to leave that one alone. This equation in the system is not in y equals mx plus b form, so I'm just going to adjust it, make it look different by solving for y. And when I do that, the first equation stays the same. The second equation, I took the 4x and sent it over to the other side. So now these are both in y equals mx plus b form. You don't have to do that, but most people would agree that's really easy to graph from there. So now, loosely speaking, and I'm going to show this to you more precisely on a coordinate grid here in a moment, I take this first equation and I graph it. There's my y-intercept of 4, and my slope is 2, so it's going up 2 over 1. So I get something like that for my first equation. My second equation has a y-intercept of negative 2 and a slope of negative 4. So that's going to do something like down 4 over 1. And there would be another point. So I get something like that. If I do this super carefully, that spot right there is going to be the answer to this system of equations. So now I'm going to take that same idea and I'm going to show it to you on a more precise coordinate grid. This is from your note sheet. Here's that very first equation. I leave it. Here's that second equation. I turn it into a y equals. And now when I graph these precisely, this is both of those lines. When they're graphed precisely, you can end up counting, for example, this one, y-intercept of negative 2, slope of negative 4, which means down 4 over 1, put a dot, or it could be positive 4 and then negative 1, put a dot. When I look at this other one, y equals 2x plus 4, the y-intercept is 4. The slope is 2, which means I could go up 2 over 1. Or I could go negative 2, negative 1, negative 2, negative 1. Well, if I'm careful about it, I find that spot, that's the intersection spot, negative 1 comma 2. That means my answer is negative 1 comma 2. Or sorry, x equals negative 1, y equals 2. Just for review's sake, if I wanted to make sure that this really was a solution to that system, I take the x and the y and I plug it into the first equation. So there's my y, there's my x. I work it out and I get a true result, but it has to work in both equations. So I take my x and my y and I plug it into the second equation. There's my x, there's my y, and I work it out and I get a true result. That confirms that this is my answer that I got from finding the intersection point of those two graphs. Let's do one more example. Okay, so in this case, let's zoom in a little bit here. Hold on. Okay, I'm going to work with this system of equations right here. And if I'm going to go ahead and graph, this is the line y equals -3. And sometimes these are more difficult to graph. They're so easy, they're difficult. This is my line y equals -3. If I go along that line, anywhere on that line, the y value is -3. Now I can graph this one of two ways. I can convert it into y equals mx plus b, or I could find the intercepts. I'm going to pause this and show both of those ways. This line's already graphed. This line I could convert into y equals mx plus b and graph it, or I could do the intercepts. So for the y equals mx plus b, I'm going to go on with this. My y-intercept is 6. My slope is -3/2, which means the line is heading downhill. And I can say -3, +2, -3, +2, -3, +2. And as I do that, and I'm very precise about it, I get this intersection point right down here. That's going to be my answer. That is the point 1, 2, 3, 4, 5, 6, down 3. That's the point 6, -3, which means the answer to my system is x equals 6, y equals -3. Boom, you're done. Had you have decided to graph this by intercepts, you would have taken this equation, said if x equals 0, that makes the 3x go away, y must become a 6. Or if y is 0, that makes the 2y go away, then 3x equals 12, x equals 4. So you might prefer graphing this way, in which case you would have put down your intercepts in 0, 6 and 4, 0. Those are actual points that you can put on your graph. And you connect the y-intercept and the x-intercept, and you extend it out, and you find the intersection point. It doesn't matter which way you graph, as long as you're accurate. You're just looking for the intersection point. Once you have the intersection point, this is the x and the y that work in both of those equations. I want to alert you to a couple of unusual things that can happen, and we'll cover these more later on in a different section as well. But sometimes you graph the first line and you graph the second line and they never intersect. You've got no solution. Sometimes you graph the first line, and then when you go to graph the second line, it ends up falling right on top of the first line. So you can kind of think of that as they're intersecting continually or forever, in which case you would say infinite number of solutions. So some unusual things can happen. Never intersect, no solution. Always intersect, infinite number of solutions. That is the graphing method.